So I'm going to be talking about how classifiers induce agents to invest effort strategically, and this is joint work with John. The fundamental thing that I want to be looking at today is the interaction between evaluation and strategic behavior. So when people are evaluated, how does the knowledge that they're being evaluated change their behavior? This often comes up in the context that we think of transparency as a goal. We want our decision-making processes and our evaluations to be transparent and obvious to the people who are subject to it. And one of the worries that this raises that comes up sometimes is that if people know exactly how they're being evaluated, they'll try to game the system in some sense. And this has come up a lot in the CS literature, actually, especially recently, where there's work thinking about how do we structure decision-making rules that either minimize the amount of misrepresentation that people can do or somehow get to the true classification that we were looking for, even if agents behave strategically and misreport their true types in some sense. And what I want to think about today is, in a sense, a little bit orthogonal to that. And it comes down to how we conceive of strategic behavior. And so for the remainder of this talk, I'll be using kind of education and assessment in education as a running example. But in principle, these ideas apply to areas like lending, hiring, and so forth. And the fundamental assumption that I want to question is, what is the ground truth? What is someone's true type? Okay? And in the context of education, the example I'll give you is we evaluate, in the US at least, we evaluate people when they're applying to college in very particular ways. Those ways are, you might say, pretty transparent or well-known, at least to some extent. You know the things that are important, the things that may not be as important. I should note that this amount of information is not uniformly distributed throughout the population. And in fact, this is where transparency does become even more of a goal in the case that you want people to have an equal amount of information into the process. And so this is also a context where people respond very obviously and strategically to being evaluated, right? Why do people optimize their GPA and care so much about it? Why do people optimize their SAT scores? It's because they're being evaluated on these things. And so there's multiple ways of going about optimizing these things. On the left here, you have at the library studying, trying to improve your GPA. And while, yes, this is in service of perhaps that ultimate evaluation, it is from the perspective of the admissions officer or the college who's admitting them, desirable behavior. You want the student to learn. You want them to prepare themselves to enter your college. On the flip side, there are perhaps less desirable ways of achieving these positive decisions. I'll bash SAT prep courses as one of those. But there's, I mean, in a sense, the SAT was created to measure some notion of aptitude. And what it has become is it's something that people optimize towards, right? This is commonly known, many of us in this room may have heard this, as Goodhart's law, which is once you define a metric and that becomes like a target, then all of a sudden it ceases to be a useful metric. But what I want to take away from this is that not all strategic behavior is undesirable, right? There are things that we want to incentivize, and there are things that we don't. And especially in the education literature, this is actually something that people are quite aware of. There's a book called Measuring Up by Daniel Kortz where he gives us this. Test preparation has been the focus of intense argument for many years, and all sorts of different terms have been used to describe both good and bad forms. I think it's best to distinguish between 7 types of test prep: working, teaching more, working harder, reallocation, and so on. The first 3 are what proponents of high-stakes testing want to see. So Kortz has identified lots of ways that people can go about trying to optimize their outcomes, and identified some of them as positive or desirable, and some of them as undesirable. And so going off of this, what I want to ask is, how can we build decision rules or evaluations that incentivize particular behaviors? Okay? And so in order to do that, for the remainder of this talk, I'm going to introduce a model, go into some analysis of that model, and see what conclusions we can draw from it. And in order to create a model, what are the ingredients that we need? Well, fundamentally, the agent needs to be able to act. They need to be able to invest effort some way to behave. There also has to be some amount of observation that the evaluator has. They need to know something, even though they don't necessarily behave exactly, or they don't necessarily observe exactly how the agent behaves. They observe some facts about this person which are influenced by their behavior. And finally, there's this evaluation rule, right? Ultimately, the agent is being scored in some way. Maybe it's the probability of getting a positive decision, maybe it's a grade in a classroom, but there's some evaluation, and I'm going to assume that that evaluation is publicly known. Okay, so the agent's going to know exactly how they're being evaluated, and they'll get the chance to behave in a strategic manner, and based on that, there will be some observation on which they will be evaluated. More precisely, it's going to be, I'll formalize it as follows. There will be M actions available to the agent, and they can invest a continuous amount of effort in any combination of these actions that they want, up to some finite budget. Okay, there will be features that the evaluator observes. And the way that those features are generated is going to be in a precise kind of functional form that I'm going to give you. And basically what I need is some way of translating action into observations, right? And so the way I'm going to do that is say every feature is you take a linear combination of all of the effort that this agent has invested, pass it through some somewhat arbitrary function. We're going to put some restrictions on it. In particular, I want it to be concave, and this is in order to get some sort of like diminishing returns of effort sort of assumption built into this. But basically, the agent will take these actions. This will generate features. And then finally, the evaluator is allowed to choose some arbitrary decision rule that maps features into outcomes, right? These can be binary outcomes or continuous. For the purposes of this talk, it'll turn out that it is kind of sufficient to consider continuous outcomes, but we'll get a little bit more into that later. And I'm going to kind of impose an orientation on this model in that more is always better. And so more effort always results in higher features, and higher features are going to result in higher outcomes. And that's in fact a restriction I will impose on whatever mechanism that the evaluator chooses. Higher feature values are good. Okay, and so I'll kind of refer to that as a monotonicity property. And if this looks somewhat familiar to you, it should. This is actually derives from a pretty standard principal agent setting, right? Principal agent setting with hidden actions is kind of exactly this, where an agent behaves in some way that is unknown to the principal. The principal rewards the agent in some way based on indirect observations. And so what we're doing here is just imposing a certain information structure, if you will, and a certain interpretation of what those observations mean. Okay? And so to make this concrete, I'm going to take us into the classroom setting, and I'll instantiate this model. Oh, and I should say, I've kind of put these alphas here. I've told you how they mathematically relate in this model, but I think the way to think of it intuitively is these alphas are like the relative rates at which a feature or an action improves a feature. So the higher alpha is, the more quickly that particular action improves that feature. Okay, so getting into this concrete model, let's say we are playing the role of a teacher, and we have this classroom, and there are two assignments. There's a test and a homework. Okay, and these scores will be what are observed by the teacher, these features FT and FW. And based on these, the test and homework scores, the teacher is going to assign a grade. And for the sake of simplicity right now, I'm going to say, let's assume that this grade is just a linear combination of the two scores. Okay? And so the teacher gets to decide what these weights beta are. What are the relative values of the test and the homework? Okay, and in this model, what can the student do? Well, we're going to say the student has three actions. In the best case, the student studies and improves both their test and homework scores. That's represented by X2. But you also have the possibility that this student just decides to cheat on the test instead, or copy off the solution manual for their homework, right? And each of those individually improves those one assignment, but studying improves both, okay? So if the setting is clear, what I want to ask is then, when can we incentivize desirable behavior? Okay, under what conditions is it even possible to set these betas such that the agent is only incentivized to study and not to cheat on the various assignments? Okay, so if you look at this for a second, you realize that there's a kind of an obvious case when things work out well, which is when it is more productive or more efficient to study than it is to cheat, right? In that world, things are great. You can essentially set the weights or the values of the test and the homework to whatever you want, right? Because at the end of the day, it's more efficient for the student to just put in the work and study. Unfortunately, the whole point of cheating is that it's easier, right? So you might not expect to be in this setting. You might instead to be in a setting like this one, where it's, let's say, for the sake of concreteness, 3 times better to cheat than to study. Okay? I'm actually going to argue that in this version of the world, there's actually no way to incentivize a student to study. Okay? And I'm going to make a pretty simple argument to do this. Basically, let's say the student put any effort at all into studying. What could they do instead? Take half of that effort, move it up to cheating on the test. Take half that effort, move it down to cheating on the homework, right? And I claim to you that this has actually only increased the values of their homework and test scores, okay? And so I'll call this notion substitutability, right? When there's one piece of effort that could actually be substituted out and put elsewhere, and that actually just only improves the scores and therefore can only improve the outcome, okay? Right, so this might seem a little disheartening because we just said the case where cheating is more efficient than studying is probably the more likely one, right? And it turns out that our main result is kind of the converse of this, which is that whenever effort is not substitutable, there actually exists what I'll call a linear mechanism incentivizing that effort. Now, remember I told you earlier that I was going to consider an arbitrary class of mechanisms that took features and produced outcomes. Basically, what this result says is that whenever there exists any mechanism that does what you want it to do, there exists a linear one that does so. Okay, and so in this example, you've seen that I've actually increased the efficiency of studying just a little bit. I've moved it up from 1 to 2. And so you notice it's still more efficient to cheat than to study on any individual assignment. And if I were to put all of the weight on the test, the student would still cheat on the test. And if I were to put all the weight on the homework, the student would still cheat on the homework. But it turns out that if I actually balance the weights between them, right, the optimal thing for the agent to do is actually to study. So unlike the previous 2 kind of cases of the world that we looked at, it actually matters now what these weights are, right? There's some sort of careful balancing act that we can do that overcomes this kind of ease of cheating in this particular example. Okay? When removing effort, like if I were, as in the previous slide, when I was pulling effort away from taking it out of x2 and moving it to x1 and x3, and that only made the features larger. Okay? And remember, as I said, I'm orienting this example such that larger features is always a good thing. Okay? And so I will attempt to give some intuition for the proof for actually how this works and why it works. Before that, I just wanted to go into some kind of consequences and sort of auxiliary things that we found by looking at this. One thing that we, yeah? Yeah, please. Yeah, so I'm hiding a lot. In particular, I told you that I was going to take combinations of these things and pass them through some concave functions. I'm going to leave those functions uninstantiated because the results actually do not depend on them. So when I said you have to do some careful balancing of the weights, that actually depends on, as you were saying, the derivatives, what that kind of diminishing return curve looks like. That balancing of the weights will actually depend on that. I'm not going to get into it for the purposes of this. Okay, so in terms of other things that you can say about this, there's certain hardness results you can get from a model like this that basically say, if you were trying to learn on top of maintaining the sort of strategy proofness or only incentivizing your desirable behavior, that constraint actually makes things computationally difficult to do. And there's kind of a badly behaved space of linear mechanisms that satisfy this incentivizability constraint. Here I've just put on this is like a kind of non-convex set of mechanisms that you get out of this. Okay, maybe if I have time, I'll get into that a little bit later. But where does this main result actually come from? I want to return to this notion of substitutability because it's actually kind of the key condition that binds on this, this model. And I've written up kind of a simple linear program here. And I claim that this is actually capturing substitutability in a kind of precise way. Let's say I'm looking at whether x sub j is substitutable. Okay, I'm going to define its substitutability to be basically this optimization is saying is how little effort could I put into the other effort nodes or the other variables while only increasing the rest of the features. So if you remember, I had this in this example, how little effort could I put into x1 and x3 to make up for removing effort from x2? Okay? It turns out in this example, if I just kind of put 1/3 into x1 and 1/3 into x3, I've made up for whatever I pulled out of x2. Okay? And so I claim that whenever this quantity is less than 1, this particular effort variable is substitutable, and therefore I can just never incentivize anyone to do it. Okay? Now, I claim that the converse of this was actually going to give me, constructively give me the mechanism that I'm looking for. Without getting too deep into the weeds, whenever you see a linear program, you think of maybe taking the dual. So if you do, in this, you kind of massage a little bit, you account for certain things, you get some sort of linear program that maximizes over something in the space of Rn, which is the number of features. This gives you another linear program, and it turns out if you solve this linear program, you actually constructively, the beta that maximizes the dual to this actually constructively gives you a mechanism that incentivizes effort into x sub j. Right, so we have this test, basically. Is this thing substitutable by this particular definition? If not, then you constructively get this linear mechanism you were looking for. Otherwise, no such mechanism exists, linear or otherwise. Okay? And then, of course, you have to, I was telling you about one particular effort variable. Of course, you can consider sets and kind of simultaneously incentivize all of them. And actually, a consequence of this is that if you look at the sets of actions that can be simultaneously incentivized, it's downward close. So if I can incentivize you to do like study and also do community service, I could incentivize you to do either one of those individually. Okay? Real quick, I'll go into some sort of hardness of optimization results that you get out of this. Let's say I know which things maybe, or I know how to test for which actions are incentivizable, but I'm actually not sure which ones are my favorite. It turns out it's actually hard to do any optimization over like the subset of variables that you choose. Without going too much into the details, basically you can get kind of a nice reduction from the independent set, and doing any sort of optimization is kind of equivalent in some sense to doing a max independent set problem. Okay, so just to wrap up, we have a tight characterization of incentivizability in this particular model, and one kind of nice consequence is that linear mechanisms actually suffice. And so maybe to counter John's original point, maybe this is an argument for simplicity in some sense. That being said, it is also hard to choose effort profiles or sets of incentivizable actions, and it's hard to learn from data subject to these constraints. In the future, there's lots of things you could do with this. In particular, I've been thinking about this problem for one agent. You could think about others. This version of the problem is deterministic. You could ask about randomness. And yeah, that's about all I have. Thank you.